Correct.
Just curious.
So date would have been a little bit different. Remember, dates are,
Strings.
these aren't strings, these are actually dates. So these are actual, that's good because I just would have forgot that. So they're black, which means they're numbers, but this is a label on top of the number, right? And this is the number of weeks since January 1st, 1960. So it's a number, a really big number. And we can kind of look up that number. Not kind of, we can look up that number. Or we can t-set the data and use the date itself. So let's see, where do we t-set it? All right. And I like t-setting the data. Because it gives us a nice picture of what it is we're doing. It tells us our date. Our data goes from December 18, 2004 to April 2nd, 2011. We know that each increment, each period is an increment of 28 days, 4 weeks. And we can use the date function. And the date function, so we would have to now remember what the date was that we're going to hold back for. So using the, we're going to have to t-set the data anyways. I mean, we don't have to, but it would make sense to t-set the data anyways. So let's see. Yes. So if we're going to use the date function, and we probably do want to use the date function, we're going to get the same results either way. So it doesn't matter. But we have to use that, can you read that? It's TD, which is our time date. So our date is going to be less than TD with a time date, which is, and it's strictly less than, so it's going to be before May 1st, 2010. And we get the same 70 observations. If we didn't do that, we would have to format the data so that it's the actual numbers of weeks since December 1st, 1960. And then we can use that big number. But this is easy. Using that time series date is just as easy also. All right, so here's our holdback sample. Let's go back.
You got that May 1st by looking at your table and counting back days?
Exactly.
Okay.
So the command we just ran gave us the exact same information as the right case time?
Correct. But if we wanted to use the date function, we would, instead of using time less than 71, we're using date less than May 1st, 2010. It's easier to use time. But as you'll see, we're going to want to t-set the data anyways. All right, now I'm going to let's see what I have here. Run my post regression command. I'm going to call it hat1. So, hat1 represents my predicted case volume based on my holdback sample, the 70 periods. And now I want to take my prediction from the holdback sample and Case did was forecast for those future periods.
I thought that was saving my regression of 70.
It is. It saves my regression of 70 for all the periods though. But it only uses the values from the 70. So we can see it. We can table it, but we can see it also. So Case's hat, you can see there, was our forecast, was our regression from our prediction from our full sample. Case's hat 1 is our regression from our holdback sample. You can see they're not exactly the same. 45072, 44430. They're different because they're based on different data sets. One had more data, the other one has less data. Let's see what this looks like. I don't know, you can't really tell much. We do know that prediction, well, let's do this. So here's all three of them. Holdback sample is the dashed, I'm sorry, the dots. The full sample is the dashed, and the actual is the blue. And I just put the vertical line there to show where the forecast starts. What we probably want to do is blow that up a bit. What does that mean? We don't really need all the data from before. We know that data exists. The model fit pretty well. But here are the two forecasts. The red forecast, using the full model, is better, more accurate than the holdback sample. Right? Neither one of them are perfect. But you can see that the dashed is a little bit below it here. The peak's a little bit lower. So they're clearly different, but they're not that different. We were pretty confident when we looked at those, the difference between the actuals and the predicted values, right? We looked at the percentage difference and we said, well, you know, there was a couple of months in which they were high, but if we looked at most of the months, those percentage differences were really small. We can recalculate those differences again, but we can see they're probably not going to be a whole lot different.
How do you get it just to output that?
The same way we got the regression to run just that 70 period. So we said regress if it's before period. Now we're saying graph it if it's after. It's after this period.
With what data?
With what?
I'm missing how we're getting our forecasted results. So you're saying graph it, but you don't have a regression to graph it off of. Are you saying forecast, or
No.
how are you getting the data?
Predict actually predicts for all the values in the data for which you have, for which the model exists. So, when we look at this model here, and this is going to become clear when we do the actual forecast. We really have two things. We have time and we have month. As long as there's a time and a month in the data set, prediction will predict for those values, whether or not we use those times and months in our regression. So what does that mean? It means that, let's go back to the data. It's magic-ish. Just a little bit. Okay, so we got the time and we got month, right? Here's time and month. Here's our prediction using the full regression. We used all 83 periods for this regression. And if we scroll down, we see that Case's hat filled in every period for which there was a time, and a month. Then we did what? We ran a regression on just the subsample of the data.
Yet it plugged it in.
Yet it plugged it in. That's what predict means, exactly. They're hypotheticals. It predicted, it didn't know that there's no data there, that there wasn't any data there. It just knew that there's a time and month, let's predict for those times and months. So even though we only used 70 observations, it filled in for the whole data set. It pretended, well, it didn't pretend, because we didn't use those final 13 periods. Now what we're going to do, what we want to do, is add 13 more periods here, and then literally forecast for the future. And that's what a holdback sample does. It acts like you don't have the data, which is run the regression, pretend we don't have the data, hold back a sample, then forecast for a period that we already know exists, and then see how those forecasts, see how well that forecast is using this holdback sample. Any other questions? I don't think this is going to work because I dropped those, but this is happening. Drop. I reused my command, so I need to get rid of that. But I'm going to regenerate those two variables that I generated already earlier. That is, I want to take the difference between actual cases and my cases hat 1, which is the regression from the predicted values from our holdback sample. That'll give us the difference in cases. Then I'm going to take that difference in cases and divide it by actual cases. That'll give us our percentage difference.
Does the dash mean the same thing as the slash?
The dash, the dash, the dash.
Between
This
two?
dash?
Yes.
Yeah, that's a minus.
Minus.
That's a minus.
Is it the same thing as down below? Because I've got gen diff 1.
No, that?
Nope, the one down there, this thing, the side.
This?
Yeah.
That's a divided by slash.
So tell me what I'm defining in the first one and the
I'm
second.
taking this value
Yes.
as the difference.
Okay.
Then I'm going to take that difference and divide it by cases. Basically, I'm looking at a percentage difference.
And why do you have to drop it before you do that?
Because I reused the names, actually I didn't have to do it, because this is diff one and P diff one, so I didn't have to drop it. I thought I reused the
Oh,
names.
if you were to use the same name, then you're
Yeah.
resetting it, okay.
Yeah, it would have told me I've got two variables of that name already, so. But essentially what I wanna do is look at that table again and see. Kind of thumb through the results. And we can graph these. But basically, we're seeing if are our results that much, do we see a lot of big numbers in there? Not really. Not really. 2%, 3%, there's an 11%, there's a 10%. So our holdback sample probably is worse than our full sample, but it doesn't look like it's a lot worse. The graph shows that they're pretty similar. Looking at these percentage differences shows that they're probably pretty similar too.
So is this in effect, we just had a holdback sample that was a regression, and those last 13 periods in the last column are essentially the forecast of the actual for the last
Yep.
13 periods.
Yeah.
Okay.
So even though we didn't use the data for these, look at the percentage difference that we're off.
Yeah.
2, 3, 4, 8. And what's the biggest going back 13 periods? So 6, 7, probably this 8 is the biggest. And again, it's a January, which we consistently, at least have underestimated.
Mhm.
So we did pretty well. The model predicted the future pretty well. The nice thing about predicting this future was that we knew the future and we can compare the future with the actuals. We predicted with the actuals. What we want to do now is predict for, well, this is an old data set, but extend this data set into the future. 13 periods, let's keep it at a year. And then forecast for that. Now, again, when we do an actual forecast, we're not going to have any way to compare those predictions until it comes through. And you do these things, when you do these things, and I've done enough of them, you're sitting there, you're waiting for the data to come in, and you can compare right then and there. How is the data compared to what you forecasted?
What's the difference between the predict underscore hat and predict underscore hat one again?
Predict underscore hat was the full sample.
Full sample, okay, and then the other one is.
Hat
just the
one
holdback
was
period.
our holdback period,
Okay.
yeah. Minus 13 periods.
Okay.
Okay. Let's do that. We t-setted the data. So since we t-setted the data, we can use this command. This data's got a whole suite of forecasting tools. Time series TS, append, add 13 periods. And what Stata does is, since we t-setted the data, it knows that these are 4-week ending periods or 28-day periods, and it's going to add 28-day periods using the actual dates. So they would match exactly the actual Nielsen data as it came in the future, if we had those. And if you don't believe me, and I'm sure you're thinking, oh, that can't be true, that's insane. How many periods do we have? Do the math. 28 days, 28 days later, 28 days. Well, this one's easy, because this one's April 30th, and this is 28 days later. So because we t-set the data and we told it that each period was 28 days, it's going to add 13 28-day 4-week Indian periods, 4-week periods. Notice we don't have cases for those periods. Those periods haven't existed yet. We also don't have what? We don't have month, and we don't have time or year. So we need to add those because our regression uses, right? So even though there is no data here, and we can't add the data, what we do need to do is add in the variables that we're going to predict for, that we're using in our model, and that's month and time. If we don't do that, the model will only predict for the periods in which those variables exist. In other words, it won't forecast into these 13 periods. So we can kind of do this brute force, just add in years. We've got the dates and the months here. Or regenerate those variables, and it's pretty easy to regenerate. And not even regenerate them. We're just going to replace them with really themselves. What did I do? We already had year, and we didn't need to do that. We already had month, which we did need, and we already had time. But I told Stata to replace year with year from the date. Now, what did Stata do when we appended the data set? It created what? Future dates. So we've got the future dates, but we didn't have the months and the years and the time to go on it. So notice the only real changes it made were what? Were 13. Which were the periods in which those variables were missing.
What's the underscore n?
That's our command for generating that time sequence. It just created a first period was 1, second was 2, third.
Like a sequential?
Exactly, it's just a linear sequence.
So, all of this so that you have kind of over there in your do file, is that when you're doing it by brute force? You're calling
Yeah.
the other?
Yeah.
Or like this better?
Yeah, I will be glad you weren't in that class. Because I hadn't introduced the t-set stuff. And when I'm doing this, I'm thinking, man, there's just a much easier way to do it. And that class must have been particularly ornery because I said, do you want to learn some new commands? And the answer was universally, no. Okay, if you don't want to learn new commands, we'll use old commands. Boom. This time I didn't give you that choice. This is much easier. Because literally what I'm doing is replace month 4. It's
Yeah.
just a pain in the butt.
Yeah.
So I took away some of your freedom, but I did it for your own good.
I appreciate
Right?
that.
I'm just looking out for your best interest. So let's go back to the data set.
You said we didn't have to replace year. I'm missing why we didn't have to do that. You did it, but you said I didn't.
Yeah, mostly because I just highlighted it and I didn't have to. It's not in the model here. Yeah. No, it could be, because we can easily replace time with year. And we get the exact same results, but it's sloppy because the numbers are so big. And using this linear sequence is just an easier thing to do. I've actually seen times when using time gets kind of messy.
So, is that month multiplied by date? Is that what that is? Or what-
No,
what does that
it's actually a function. So it's saying replace month with month from the date, from the variable date. And the variable date, when we TS appended and added those 13 periods, we created the variable date for those 13 new periods.
That makes sense. But that wouldn't work.
Yeah. So remember, these weren't here before. All three, none of those three were there. And we said replace year with year from the date and month from the date. And then we just added the sequence. And the reason why Stata said only 13 real changes were made is because when it replaced all of them. But 83 of them were the exact same values that were there before. So that's why it said only 13 real changes were made. Even though it replaced it did it 96 times. In only 13 instances were there changes. And those changes went from blank to something. Yep.
You created a regression with date, but could you just append date with time still selected with that regression?
Yeah.
You can still do it, okay.
It's just easier to pull these out. We could have done it by hand like I showed you, like I told you about. But it's easier just to pull it out from the date function. Now we're good to go. Now we can run our regression. We've got our future time and our future months. We're going to run the full regression on all 83 periods and then forecast for the future. And we should be able to get future values. And just to make sure that I think I'm hiding them over here. That's it. So we're going to predict for the future, and we'll call it cases hat 2 probably, I imagine. And it should fill in for all 96 periods of the data.
Will that be the only column because you don't have real data for the other two, for cases in hat 1? Hat and hat 1, you know what I mean? How it filled in for the other one? Is it gonna backfill those that it doesn't have?
No, we're going to generate a new cases hat 2, and it shouldn't affect it's not going to affect anything else. But that's all we want are those future values, future forecasted values. All right, so let's close that down. We're going to run our exact same regression with no. Right, we've got the full data set, all 83 observations. We're back up to our same 93R squared. This is the same regression we started with. Yeah, and December wasn't statistically significant in our full regression either. Now when we predict, it's going to predict for every observation for which we have both a time variable and a month variable, which we made sure we filled in that data set. So I'm going to predict it, and as I anticipated, I'm going to call it hat 2.
Reason why you call it hat.
Why do I call them hat? Because usually when we talk about predicted values, we denote it with a hat. So actual is cases, predicted is considered with the limitation. Or I like to wear hats. I actually don't wear hats. Yeah.
So that just filled in all our predicted values for the new data?
Hopefully, let's check. Wouldn't be the first time I messed up. All right, but the real trick comes down if it goes. The suspense is just killing you, isn't it? So now we've forecasted for the future, right? Even though this future's past. That's our forecast.
So then do we only graph the last?
Yeah, I would say so. I mean, we we can kind of see how it fits the trend, kind of answering the questions that we've been asked before. All right, the dots are the actuals, and I didn't connect them because I wanted to clearly demark the predicted, but the dots are when the data, right? The data ends right here. So there's no more data. And then our trend continues on the same trend that was existing for those previous years. And our seasonality continues on in the same way that the seasonality occurred in the previous years. So the question is, kind of back to his question, was, if we believe that this trend is going to continue on, then this model should be pretty accurate. But you're right, we really don't need all of this. What we want are these values. What we want are those values. Those are forecasted values. That's something you get, like I said, paid to do. Let's see what this looks like. For some reason I connected the dots. Yeah, I connected them. I should have cut them off somewhere, but I didn't.
And once again, a two-way function, what does that indicate?
What the two-way did, what I did with the two-way is, well, let's go back to the graph. Two-way allows you to superimpose one graph on top of another. So essentially what I did with two-way was I constructed this graph of the actuals, and then I constructed this graph of just the predicted because I wanted the color to be different, to clearly distinguish the predicted from the future from the past values. And as far as I know, there's no way to say change color at some point in time, so I just superimposed two different graphs on each other.
Therefore, is it like a three-way, four-way, and so on?
No, two ways as far as it goes. All right, what are we going to do now? We generated a forecast, and what do we generally know about forecasts? They're wrong. Exactly. So we have to include some margin of error. Right? If I forecasted 24,267 cases are going to be sold the next 4-week ending period. That's what my forecast said. That's what my regression said. And it was a really good regression. And I got in this is the forecasted. Data comes in from Nielsen, and my actual is 263 cases. Was I right?
I would say.
No. No, I'm wrong.
It's awful close.
It's awfully close. It's excellent, but it's still wrong. And at what point in time do you say, wow, that's really close? At what point do you start saying, that's not so close? Your forecasts are kind of off. So we want to construct that. We want to add plus or minus some margin of error. We acknowledge that no forecast is going to be perfect. We acknowledge that no forecast is going to be perfect. But as long as we're within some tolerable margin of error. And we let the client choose that margin of error. I want a 95% confidence interval. I want to be 95% confident that your forecasted value, that the actual value is going to come within some margin of error of your forecasted value. This probably satisfies that, although we haven't done the math yet. We just want to account for the fact that our forecast is going to be imperfect, but as long as we're within the margin of error, we'll be fine. Hence, we got to go back to the PowerPoint. All right. So there's our hat values, our predicted value, plus or minus some margin of error. And that is the formula for the margin of error. It's kind of nasty. But it turns out that Stata will generate this forecasting error, at least that part of the forecasting error, by using the command predict, and this is not a command, this is the name I'm giving it. But we need to use the option. Remember, predict will save the regression, but if we add this option STDP, it will generate what's called the standard error of the prediction. So I gave it the name SEP, standard error of the prediction. It's a post-regression command. Remember, if we use the command predict SEP after we run a regression, what would SEP be?
Same version.
It would be the regression. If we put the comma, the option STDP, then it tells Stata to save me the standard error of the prediction, which is that formula thing. Otherwise, you have to do it by hand. We don't want to do that.
So going back to that other example, if I had done predict cases underscore hat 2 comma STDP, it would give me my numbers and this number,
No, it would give you the standard error of the prediction.
and not those other values.
Nope. We already have, so we already have y hat, so p. Those are our predicted values. That's what the p stands for, predicted values. This other term, the margin of error, is really two parts. One of them is this mathematical formula called the standard error of the prediction. The other one is our t-value, which is really dictated by us, in that we're going to set some level of significance called alpha. And that sets our, what we're called our confidence interval. So usually we have a 1 minus alpha % confidence interval. What the heck does that mean? The standard level of significance is 5%, which means you're going to have a 95% confidence interval. What does that mean? It means the margin of error, right? As we increase our confidence interval, really the usability of our forecast becomes useless. For example, if I wanted a 100% confidence interval, I wanted to be 100% certain that my actual cases fell within the margin of error of my predicted cases. If I wanted to be 100% sure that my actual cases fell within the margin of error of my predicted cases, what would my kind of upper and lower bounds be for my confidence interval? How would I be absolutely 100% certain that my forecasted values, I'm going to set a confidence interval, this upper and lower bound, between which I want to be 100% sure the actual value falls. What would you set those values at? And 0 and 0?
0 and infinity?
0 and
Infinity.
infinity. Exactly. Kind of double zero, right? I'm pretty certain, no, I'm 100% confident that next month's sales are going to be between 0 and infinity. That's kind of ridiculous, isn't it? That margin of error is too wide. It's absolutely useless. Are you going to be correct? Yes. Good for you. You provided absolutely no value to the company. So we're going to reduce that confidence interval to something pretty manageable. Let's call it 95%. And within 95%, that confidence interval is going to get narrower and narrower. Right? And we can change that confidence interval by changing that t-value. And yes, that's the same t-value, or it's related to the same t-value that we look at when we look at t-statistics for statistical significance. So alpha is going to be our significance level. You can see it there. DF is degrees of freedom. I think I would put all this in the PowerPoint. So here we go. Yeah, depends on two things. Degrees of freedom, which is n minus p minus 1, which is basically the number of observations we have, the 83, minus p, the number of variables in our model, whatever that is, minus 1.
And was the number of periods?
Number of periods. What you're seeing on the screen is completely different than what I'm seeing on the computer. It's bizarre. Do you got that? I need to change it.
What would you say P was again?
Excuse me?
P was what?
P is the number of variables in the model, so we're going to look at that real quick. All right. N is the number of observations, the number of periods in the model. P is the number of variables in the model. So we can just count. We got 11 of these, right? 12 minus, we have an omitted category. Then we got time, so we got 12 total, minus 1. So N minus P minus 1. Which will give us 70. So we have 70 degrees of freedom in this model. Degrees of freedom equals 70. We'll use an alpha of 5%. Because we have a two-sided confidence interval, in other words, an upper and lower limit, we're going to have to divide that by 2. But that's fine. So let's do that first. So the command is display, which is just that. bracket facing the wrong way. All right, so it's display, and it's inverse t-tail. So INV T tail. Display inverse t-tail. The first number is the degrees of freedom. And that's going to change from model to model, right? We're going to have more observations or less observations. We're going to have more variables, less variables. So degrees of freedom is going to change. We're choosing a 5% level of significance because our confidence interval is going to be two-sided. In other words, we want to have an upper and lower limit. We want to have an upper and lower limit from which we can compare our actuals with our predicted. Did the actuals come within our margin of error of our predicted? Because we have, and confidence intervals aren't always two-sided, but because we have a two-sided confidence interval, we divide that by 2.
Can you tell me how you calculated the 70 again?
Number of periods
Okay, 83?
minus the number of variables in the model, which was 13, minus 1. I'm sorry, which is 12 minus 1. Because we had 11 months and then time. All right.
So N periods, P variables.
Correct. And then 1. All right, so let's construct that margin of error that we had the formula for. We use our predict command. Post regression, so it'll remember the regression. We don't have to run it again. What did I call it? SEP? Which is the standard error of the prediction. And again, if I hit return now, it'll just resave my regression, my predictions. I have to give it that STDP, and it will actually construct a new variable. And if you can kind of see it, actually Stata gives it, well, cases hat is our fitted or our predicted values, and SEP is the standard error. If you've read the whole, you can see the whole thing. It says it's the standard error of the prediction. I hate doing this, but let's see if I go back. Yes. No. Ready to do that. So I take my standard error of the prediction, I multiply it by that t statistic, and that gives me my margin of error. So I just do the math.
Gotcha.
Gotcha. Oh. Yes. So I'm going to generate a new variable called MEP. Guess what that stands for? Margin of error of the prediction. It equals my SEP, which I generated in Stata, times, I could do one of two things. I can copy and paste that number,
Do the equation.
or I can actually use that function, yeah. And just to show off, I'm going to use the function. Oop, I got an 8 there. I meant to do that. So, let's go back over here. I generated a new variable, and it follows that formula, which was the standard error of the prediction times my t statistic, which I chose based on the sample size, degrees of freedom, and our level of significance that we're looking for. if I chose a higher level of significance, for example, 1%, it would give me a wider confidence interval. And we could do that. If I chose a lower one, it'll give us a more narrow confidence interval, but 95 is kind of standard. All right, we're almost done. Well, let's do this. Well, we're almost done. Let's now do the that part. What is that? Plus or minus. So we add it to our predicted, we add our margin of error to our predicted value to give us an upper limit on our forecast. We subtract it from our predicted value to give us a lower limit of our predicted value. More math. But Stata does the math. Believe me, it's going to be worth it. All right, so let's generate, let's call it a lower confidence interval, LCI, and it equals our predicted value, which is it cases hat 2? Yeah. Minus the margin of error. And then I'm going to generate my upper confidence interval. That equals cases hat 2 plus my margin of error. So, what did I do? I took my predicted value, subtracted the margin of error to give me a lower limit, took my predicted value, added the margin of error to give me an upper limit. So now I've got these upper bounds, which contains my 95% confidence interval, my forecasting margin of error. Let's see. This is killing my back. And I gotta save my back. All right, so I'm going to do this table. What is it called? Date. Contents. Have we used table yet? Yeah, we use table all the time. It's one of our favorite things.
What's the indicator?
Content. And you've got to tell table to calculate some statistic. We're just going to use mean. These are actually constants, so there is no variance. You know. Now, what do we got? This is gold. This is what you get paid for. Predicted margin of error, lower and upper confidence interval. I should put actuals in there too, so let me regenerate that sucker. 1, 2, 3, 4, I've got one more. Mean cases, right? All right, so let's just look at let's look near the forecasting period. All right. So let's go to 5,000 cases here. That was the actual number of cases sold in April, for the week ending April 2nd, 2011. The forecasted value was 50,000, forecasted value was 51,875. The margin of error for 95% confidence interval is about 2,000 cases. So we add and subtract that, and we can say that with 95% confidence, we should have expected somewhere between 49,815 cases and 53,935 cases. Did the actual cases come within our margin of error? Yes. We can go back and look and see how well our model predicted based on our confidence interval, our 95% confidence interval. If it looks pretty good in the past, we can kind of say, well, all right, in March, for the week ending of March 31, 2012, we're forecasting 55,000 cases, 574. Margin of error is about 22,000 cases. So if actual cases come within 53,358 cases on the low end, 57,789 cases on the high end, then our forecast will have been accurate. Does that make sense? So now we've accounted for the fact that we know our forecast is going to be wrong. We're 100% sure in that. We're not 100% sure in a whole lot of things, but we know we're not going to get exactly 55,574.2 cases. We're not going to sell that many on week ending March 31st, 2012. We know we're going to be wrong. Even if this is 0.3, we're still off by a couple bottles, right? But it's within the margin of error. It's within our forecasting error. That's what a forecast looks like. That's how you do a forecast. Demands I already did. Now you can't really see it, but notice the margin of error follows the forecast. The reason you can't see it is because we've got all this in the way. We don't need any of this. So we should just graph that forecast along with the margin of error and be done with it. So I left some actual data so we can see that it's following the trend. We skipped that period there, and you can see how the margin of error follows the trend as well as the seasonality. Why? Because our model includes a trend and the seasonality. That's it. We should be clapping. At least for the fact that we're almost done. Yeah. One of your cohorts, one of your classmates from a previous cohort, from this class alone, is now the head of forecasting at the American Academy of Sciences in San Francisco. A huge deal. He took this class and he just took to it like water. And no, California Academy of Sciences, that's right. I have no idea what I'm talking about. California Academy of Sciences, where you go see dinosaur bones and stuff like that. But they're forecasting revenue and attendees and all that stuff. And now he's the head of forecasting. Any questions? In the end, it was pretty, I mean, what we did was pretty quick. We predicted what we've been doing. The only new thing we did today was we added periods, append, and we generated that margin of error. But outside of that, 90 whatever percent of what we did today was regression-based stuff that, like I said, we did this model, problem set 1, no, 2. Problem set 2 we did this model.
Can we see your command for doing a two-way scatter and then creating your upper and lower?
It's really big and really long.
Well, ignore the legend stuff. Yeah, the legend.
Yeah, but all you're doing is the same thing you've done before. So in other words, it's exactly scatter. Now you've got x1, x2, x3, x4. I'm sorry. Let's call them y's. y1, y2, y3, y4, and then x is our time. We'll just do that. Actually, let's just do this. Faces hat. Couldn't make that connection. We got the hiccup guy again. Where's it go? Did we find out?
You have your actual
Okay, so you can put, yeah, we did it here. But remember, for the forecast, it's not going to be, so cases hat, then you can have LCI, and then UCI, and then time, or date.
Do you put cases before cases hat to get the actual?
Correct. Actually, it doesn't matter which order.
Okay.
You can rearrange these any way you want as long as they're all before date.
All before date.
The last variable you have there is going to be the x-axis variable. So, but the order of these doesn't matter.
And then you would just put in if date equals greater than.
For this graph, I'd put, excuse me, if date greater than 2010 or something like that, because we didn't need 15 years or whatever we had of data. We just need to show, look, here's the trend. It's going to follow that same trend. Sometimes I put the actuals, sometimes I don't. Usually the client will, we'll have some recommendation one way or another. But it really doesn't matter because it's that table that they want. That table is the values that they can plan for in the future. We know that we're going to get so many cases, we're going to sell so many cases next period. We can plan for employment and resource costs and all those kinds of things. So
Is that cases hat at the cases hat 2, right?
2, yeah. I think we had 3 cases hat. We had cases hat 1, and then cases hat 2.
Tableau, is that a part of our assignment?
No, so do this. Download Tableau. I'll email you guys out a passcode, and then we'll play with it and kind of see what it does next week. It actually does forecast using pretty much the same model as this. All with drag and drop stuff. So it's really cool.
Yeah.